In this section, we're going to talk about measures of variance, and we're going to talk about how spread out our data is. And we're going to focus on two things. We're going to focus on standard deviation and standard variance. Mostly, we're going to focus on this idea of standard deviation. We'll talk about why that is a little bit in class. When we talk about standard variance and standard deviation, again, we're going to talk about our population versus our sample. For standard variance, this is our symbol for standard variance of the population. This would be standard variance of the sample. Standard deviation is just the square root of that. So this would be my symbol for population, and a lowercase s would be my symbol for the sample. What the formula is for this, if I'm looking for my standard variance, my formula is going to be s squared equals, now we're talking about the sample here because that's typically what we're going to focus on. The summation of x minus x bar squared, which is basically just saying take all your values, subtract the mean, square that, and then this symbol here is called a summation. It says add them all together. And then you're going to divide by the amount of numbers in your list minus 1. And we'll look at an example of that in 1 second. What we're going to focus on when it talks about standard deviation is how large is your standard deviation in regard to the mean? Well, if you're talking about a large standard deviation, basically what we're going to be talking about here is very spread out data. So the larger the deviation, the more spread out the data. The smaller the deviation, the more condensed it is, or the less spread out. So those are important to think about here. Now, when we talk about this, it's hard to look at a standard deviation and decide, is it large or is it small? This is always in regards to the mean. Okay? If I have a standard deviation, for example, of 5, well, if that talks about how spread out the data is, but my mean is 7, well, 5 is very large in comparison to 7. If my x bar, on the other hand, is 7,000, 5 is not that big. So then a standard deviation of 5 in this example would represent very spread out data, where in this example it would represent very condensed data. So some of the uses of standard deviation are, first of all, to tell us how spread out our data is. It's also going to be used to help make predictions about things. If I'm talking about a standard deviation of 5 and an x bar value, a mean of 7,000, well, I can sort of look at the idea that my data is not very spread out. So a number like 6,997 makes sense, where a value of maybe 6,897 is just too far off, because this represents a very small, very condensed data set. A number like 6,800 and something would just be way too small to be inside that set. If you're looking for a rule of thumb here for my standard deviation, another way to get this, and this is just a rule of thumb, is simply take your range, your max minus your min, and divide that number by 4. Let's look at one example, and we'll talk more in class about it. So in this situation here, we have our list of x values. We find our mean, 8. We take all these values. So 5 minus 8, we get negative 3. 8 minus 7, we get negative 1. 8 minus 8, 12 minus 8, and we have our numbers here. The formula says that we square those numbers. So 9, 1, 0, and 16. Notice that all these numbers are positive. Your standard deviation will always be a positive number. It might be 0. It might be 0, but typically it will be a number larger than 0. So this symbol we said was the summation. It says add them up. 9 plus 1 plus 0 plus 16 is going to give me 26. So my standard variance is going to be the summation, so 26, over it was n minus 1. So in this case, I have 1, 2, 3, 4 numbers. So 4 minus 1. So my standard variance is going to be 8.3 repeating. For me to find the standard deviation, I would just take the square root of that. So the square root of 8.3 repeating, when I round it off to 1 decimal place, is going to give me 2.9. I have a mean of 8 and a standard deviation of 2.9. Since 2.9 compared to 8, it's not really that small, but it's not really that big. This tells me that my data isn't very spread out, but it's also not very condensed, because if you look, there's a pretty big disparity between 5 and 12. Obviously, you looked at a very small sample here, very small set. These numbers don't tell us a whole lot, but this is just one example of how you would go ahead and get the standard deviation. So we'll talk more about this in class tomorrow. The last thing we're going to focus on here, and we're going to skip over Chebyshev's and the empirical rule for now, is the Pearson's coefficient of skewness. We talk about skewness a little bit in class. We've talked about how there's left skewed, right skewed, positive, negative, things like that. The question is, how skewed is our data? Well, we have a formula here. And our skewness number, our Pearson coefficient of skewness, is pretty simple to calculate. It's going to be 3 times my mean minus my median. So we're looking at how much the mean and the median differ, because we know that if the mean is a lot higher than the median or a lot lower, that's when we're talking about skewed data. Triple that number and then divide by the new standard deviation that we just got. Typically, this number is going to be somewhere between -3 and +3. If you're talking about a skewness of 0, that means that your x bar and your median were exactly the same. This would be perfectly symmetric data. The farther away from 0 that goes, the more skewed the data. Typically, what we say, rule of thumb, is that if your skewness number falls between -1 and +1, you're talking about relatively symmetric data. If it starts to get beyond -1 or beyond +1, it starts to get closer to these extremes, that's how much more the skew the data happens to be. So if you have a data set that has an x bar of, for example, 12, it has a median of, we'll say, 18, and a standard deviation of 2, well, my Pearson coefficient says 3 times 12 minus 8 divided by 2 minus 18. This is going to give me a Pearson coefficient that is way, way, way off the charts. Well, since my Pearson coefficient is way off the charts, this tells me that this data, not only is it skewed, it's very, very heavily skewed to the left-hand side.